This video will introduce you to the topics of specific heat and the heat equation. The first thing we need to do, though, is to define heat. What is heat? Well, in science, we have a precise definition of heat that varies from the way we use this word in English. Heat is a form of energy. We often use the lowercase q to denote heat. Like all forms of energy, we can either use joules or calories as our units. The most important thing for you to learn is that when we are using heat in science, we are not talking about temperature. Temperature is a measure of how fast molecules or atoms are moving. Adding heat energy to a substance can increase its temperature, but not always. Remember, heat is energy and it is measured in joules, and temperature is measured in degrees C, K, or F. The specific heat of a substance is defined as the amount of heat energy required to raise the temperature of 1 gram of that substance by 1 degree Celsius. It's called the specific heat because it specifies the amount of the substance. The specific heat of water is 4.184 joules per gram per degree C. Now let's translate the definition of specific heat into an equation. This is what that equation will look like. So, the definition said that the specific heat is equal to the amount of heat energy, Q, which is measured in joules. The equation also mentions the amount of substance, its mass, which is measured in grams. Finally, it measures a rise or change in temperature, which is what the Greek letter delta means, which is measured in degrees C. All right, let's talk about the heat equation. This can be derived from the specific heat equation by rearranging the variables to isolate Q, the heat, on one side of the equation. To do this, we can multiply both sides by the mass and by the change in temperature. We can now see that the mass variable cancels out, as does the temperature, the change in temperature. On the right side of the equation, we're left with delta T times mass times specific heat equals Q. This is how the equation is normally written. Now that we've found these equations, what can we do with them? Here's a problem that you might run into in your homework or in lab. A metal object was placed into 156.3 grams of water, which was at a temperature of 23.4 degrees C. The water temperature increased to 27.6 degrees C. How much heat was transferred to the water? Like all problems, we first have to determine what the question is asking for. In this case, the answer is heat. We have a handy equation for that, the heat equation. In order to find Q, the heat, we need to know the other parameters. We can look up the specific heat of water. The problem gives us the mass of the metal, and we can calculate the temperature change, which was 4.2 degrees. The initial temperature of the water was 27.6 degrees, and the final temperature was 23.4. Putting all of these into our equation gives us the calculator answer of 2,746.6 joules. We went around this to 3 sig figs because that's what they gave us in the problem. And so our answer is 2,750 joules. Let's try another problem. The metal object from the previous problem started at a temperature of 97.4 degrees C. Both it and the water temperature ended up at 27.6 degrees C. The mass of the metal object is 152.645 grams. What is the specific heat of the metal? So what are we trying to solve for? In this problem, they're asking for the specific heat of the metal. So we will use a specific heat equation. The problem gave us the mass of the metal, and we can calculate the change in temperature. The final temperature was 27.6 degrees, and our initial temperature was 97.4, giving us a 69.8 degree drop in temperature. But what about the heat transferred, Q? All of the temperature rise in the water was due to the heat transferred from the metal. The heat gained is equal to the heat lost. The negative sign here just shows that the heat was lost from the metal. So, if we look back at the previous problem, we can now see that Q for this example is equal to negative 2,750 joules. We have everything we need to calculate the specific heat, which is equal to 0.258 joules per gram per degree C.